So now we're going to learn a third type of factoring. We've already done the common factor, which remember we always have to try to do first. Then we learned actually the fourth, because we did the complex and the simple trinomial factoring. Before we start to factor though, we're going to go back and we're going to do a little expanding. We're going to have three different equations that we're going to expand. And you may notice something about them that is similar, but we'll just start by expanding, remembering to multiply each term in the first bracket by each term in the second, and we get x squared plus 4x minus 4x minus 16. And then we simplify by putting terms together alike. Now here you notice the 4x and a negative 4x can go together. When they do, we get 0x, which is just 0. So we end up with x squared minus 16. Now usually we would expect that when we expand a binomial, which is 2 terms times 2 terms, we end up with 3 terms, but this one was only 2. So now I'm going to go ahead and I'm going to expand the second one. X squared plus 3x minus 3x. We have the same sort of thing happening here. Those two add together to give me 0, so I end up with, again, 2 terms, x squared minus 9. And now I'm going to the last one, same deal, x squared minus 2x plus 2x minus 4. Oh, same thing's happening. X squared minus 4. So this is like a special case of expanding binomials where if you notice the two binomials that we are expanding, they're exactly the same as each other except for one thing, and that is the fact that their signs, the signs in the middle, are opposite. Other than that, they're the same. X, 4, 4, minus plus, minus plus, plus minus. And when that happens, when you expand, the middle terms always add up to 0, and we end up with just 2 terms. Now what do we notice about these 2 terms? First of all, we look at the number at the end. The 4, the 9, and the 16 are all what we call perfect squares. That means you could take the square root and it would be a whole number. And that's because, of course, we always multiplied the same number by itself in each case. The second thing that we notice is that the sign in the middle is always a negative because they're opposite signs here, so it always ends up being a negative number left. And then the x terms always cancel out. Now, these are one of my favorite things in math, are these little brackets that look the same except for the sign in the middle. They have a special name. When there's 2 binomials that look the same but have opposite signs in between them, we call those conjugates. And conjugates are cool because when you multiply them out, you get these nice simple expressions. Now, that's expanding. And remember, expanding is going this way. Factoring is going the other way. Factoring is when we start with the expression looking like this and we end up with 2 brackets. So this type of factoring that we're doing here is called difference of perfect squares. And that's because we're going to be factoring these, and you'll notice there are 2 terms, not 3. It's always a subtraction, and it's always 2 perfect squares. The x is a perfect square, square root of that would be x, and that would be 2, square root of that would be 3, square root of 16 is 4. So the trick is to recognize that that is what you have. Because when you have a difference of perfect squares and you want to factor them, you just have to look and say, oh, these are 2 perfect squares of subtraction. I know where this came from. This came from the conjugates, where you take the 2 square roots, one is a minus and one is a plus. And of course, it doesn't matter if that's plus and that's minus. They have opposite signs. So, for example, if we look down here further, we're asked to factor. Now, this time we're trying to change this back into its brackets. And because you notice it's 2 terms, not 3, the other one we had, well, first of all, we'd look for a common factor, but there is no common factors. But it's not 3, it's 2. If it's 2 terms, you might think, well, maybe it's that special case where we had the conjugates to begin with, and then it ended up canceling out the x values. So we look, are they perfect squares? Yes and yes. Is it a negative sign? Yes. Okay, so this came from the conjugates. What conjugates were they? Well, we'll put down the 2 brackets, and we'll remember that it's, first of all, square root of x squared is x. The square root of 25 is a perfect square because it's 5 is the square root. 1 gets a plus, 1 gets a minus, and these are the conjugates that came from. So it's really quick and really easy. We love factoring these ones. Okay, so let's try the next one. Now remember, we always have to look for a common factor, and we have one this time. We didn't have one last time. 2x squared minus 8, we can take out a 2. We always try to remember to do that. That's a very important thing, because otherwise we don't have a difference of perfect squares there, do we? Because 8 is not a perfect square, and neither is 2. But once you take the 2 out, what we're left with here, 2 terms, that's a perfect square, and so is the 4. Meaning we can change this back into 2 conjugates multiplied together, x and 2, one with a plus sign and one with a minus sign, and then we're finished. Okay, one more example. Again, we would look for the perfect square, the common factor. 4 and 81 do not have any common factors, and x, there's no x here, so there's no common factors. So now we're looking at, is this 3 terms? It's not 3, it's only 2. So we'll look, is this a difference of perfect squares? Because if it is, it could have come from its original conjugates. We say 4x squared, is that a perfect square? Well, x squared is 4 a perfect square? Oh, yeah, it is. 2x times 2x would be 4x squared. And 81 we know is a perfect square. It's 9 times 9. And it is a subtraction, so we're good. 2x and 9, one with a plus and one with a minus. So that's how we can factor 2-term expressions when they have a subtraction sign and 2 perfect squares.